I want to look at a few more examples that utilize the product rule and the quotient rule. And just remember that we're still at the end of the day, we're finding derivatives. When we use the product rule and the quotient rule, it still tells us about rate of change, or it still tells us about slope of the tangent line, and I don't want to lose sight of that. So here for this first example, find f prime of x in the equation of the tangent line at x equals 0. Again, we should kind of be sick of this problem by now. We've seen it so many times. So I'm going to start by finding the derivative. Let's do that first. So f prime of x, I look at this, I see x squared minus 4x plus 2, and then I see times e to the x. This is absolutely going to be a product rule. So keep an eye out for if we're mixing and matching, say, polynomials and exponentials or polynomials and logarithms. Anytime we're multiplying two separate functions together, we are going to have to use the product rule in order to take the derivative. So f prime of x, so the derivative of, let's see, x squared minus 4x plus 2, that'll be 2x minus 4, times e to the x, plus the product rule is addition here. Now I'm going to leave x squared minus 4x plus 2, we'll leave that alone, so x squared minus 4x plus 2, times the derivative of e to the x. Well, the derivative of e to the x is just e to the x. We can clean this up here. I'm going to go ahead and, you know what I think I'm going to do actually? I'm going to factor out this common factor of e to the x that I have. Let's factor that out and see what that leaves us with. That's going to leave us with 2x minus 4 plus x squared minus 4x plus 2. And then I can combine some like terms here. I've got e to the x times x squared minus 2x minus 2. I think that's a whole lot easier for us to be working with. So this is my derivative, f prime of x. So I've done this part. I found f prime of x. Now I need to go and find the equation of the tangent line. Just like every other equation of the tangent line problem, I need an x value, I need a y value, I need a slope. So we just did all this work to find the derivative. Let's go ahead and use that to find the slope of the tangent line. I'm going to take my x value of 0 and plug that into my derivative. So f prime of 0 is equal to e to the 0 times 0 squared minus 2 times 0 minus 2. I know that anything to the 0 power, that's going to be 1 times 0 minus 0 minus 2 will give me negative 2. This is my slope, so my slope is negative 2. And then I also need to find the y value, and for that, I'm going to look back at the original function, f of x. I'm going to take my x value of 0 and plug that into my original f of x. So f of 0 is equal to 0 squared minus 4 times 0 plus 2 times e to the 0. This is 0 minus 0 plus 2. E to the 0, we just said that was 1. So this is a positive 2. Here's my y value. I've got my x value. I've got my y value. Got everything I need. Got my slope. So let's see. Let's do this in a different color. Y minus my y coordinate is 2 equals m. That's negative 2 times x minus my x coordinate is 0. Y minus 2 equals negative 2x, so y equals negative 2x plus 2. There is the equation of my tangent line, along with the derivative that I found earlier. So we use the derivative the same way, even though we have to use the product rule and the quotient rule to find it. It still tells us the same pieces of information, and we still interpret it the same way. Next example, I want to find the derivative, and I want to find the values of x, where f of x has a horizontal tangent line. So here, I look at this, I see f of x equals 5x divided by x squared plus 10. I see that fraction right away, and that's what tells me, okay, if I want to find the derivative, first of all, I'm going to have to use the quotient rule. So f prime of x, if I want to take the derivative here, my quotient rule, remembering, says low d high, so low. that's x squared plus 10. D high, derivative of my numerator, that would be just 5. Minus high, that's 5x. D low, derivative of my denominator, derivative of x squared plus 10, that would be 2x. All over x squared plus 10, quantity squared. Square the bottom, and away we go. So first we need to simplify that numerator. We need to kind of clean that up. So we can distribute the 5. I've got 5x squared plus 50 minus 5x times 2. I've got 10x squared divided by, 10x squared, not 10x to the 0. 10x squared divided by x squared plus 10 quantity squared. We can combine our like terms, so our derivative f prime of x is negative 5x squared plus 50 divided by x squared plus 10 quantity squared. So there's the first part of my answer. There is my derivative. I also want to find the values of x where f has a horizontal tangent line. So remember, we see horizontal tangent line. First of all, we see tangent line. I'm thinking about the derivative f prime. Horizontal, I know that a horizontal line has a slope of 0. So I'm going to take my derivative that I just found, set it equal to 0, and solve for x. So I've got negative 5x squared plus 50 divided by x squared plus 10 quantity squared. This is equal to 0. Now there's a few different ways you can think about this. I think most of us would probably just say, well, let's multiply. I gotta get this to get rid of that denominator. So I'm gonna multiply both sides of my equation by x squared plus 10 quantity squared. Now on the left-hand side, I'll end up with negative 5x squared plus 50, just cancels. On the right-hand side, I have 0 times x squared plus 10 quantity squared, but 0 times anything is just 0. So let's see, we'll add 5x squared, so 50 equals 5x squared. We'll finish up over here just so we have enough room. Divide by 5, so 10 equals x squared, and then take the square root. I end up with x equals plus or minus radical 10. Not really going to simplify nicely here, but at x equals positive square root of 10 and negative square root of 10, I know that I have a horizontal tangent line, which again, those are going to be really important points for us in the next chapter, so we want to make sure we feel comfortable with this process. So again, even though I used the quotient rule, I still use and interpret the derivative exactly the same way. It doesn't change the flow of kind of the rest of this problem, right? It doesn't change how I find the x values where I have a horizontal tangent line. It just changes how I find the derivative. Let's look at one more example here. I have a drug that is injected into a patient's bloodstream through her right arm. The drug concentration in milligrams per cubic centimeter in the bloodstream of the left arm, t hours after injection, is given by C of t equals 0.14 t divided by t squared plus 1. So I'm going to start this problem. I need to find the derivative. So I need to find c prime of t. I want the derivative of this function here. I see that fraction. I immediately think quotient rule. So the quotient rule says low, that's going to be t squared plus 1. D high, derivative of my numerator, that's 0.14 t, derivative of my numerator just 0.14, excuse me. Minus high, that's 0.14 t. D low, derivative of my denominator, that would be 2t. Square the bottom, that's t squared plus 1 quantity squared, and away we go. So now we just need to simplify this expression. So I can distribute 0.14, this is 0.14 t squared plus 0.14. Over here I'm going to have negative 0.28 t squared divided by t squared plus 1 quantity squared. Combining my like terms in my numerator, I'm going to have, let's see, 0.14 minus 0.14 t squared divided by t squared plus 1 quantity squared. And again, I could factor, I could do all sorts of stuff with this, but I think this is perfectly fine for your derivative. Last thing I want to do in this section here, I want to find c of 0.5 and c prime of 0.5, and then interpret those results. I want to be able to talk about what they represent in the context of this problem. So let's start with c of 0.5, and I'm just going to take 0.5, plug that into my original function up here. So c of 0.5 is equal to 0.14 times 0.5 divided by 0.5 quantity squared plus 1. So let me crunch some numbers here real quick. 0.14 times 0.5 divided by 0.5 squared plus 1. What do we got? We got 0.056. So what does this represent? This is, let's see, the drug concentration in milligrams per cubic centimeters in the bloodstream of the left arm T hours after injection. So this is telling me the drug concentration in the left arm. And this is telling me that 0.5, so half an hour after injection. So you can say 0.5 hours after injection, or you can say a half hour after the initial injection. The drug concentration in the, I already forgot if it was the left or the right arm. In the left arm. In the left arm is 0.056 milligrams per cubic centimeter. So this quantity, when I interpret this quantity, I'm not talking about whether it's increasing or decreasing. It simply is this value. It is 0.056. However, when I go to find c prime, that's when I talk about rate of change. So let's find c prime of 0.5 now. So c prime of 0.5, and I'm going to plug that into the derivative that I found just in the last step. So let's see, 0.14 minus 0.14 times 0.5 squared divided by 0.5 squared plus 1 quantity squared. I will say, if you're using a graphing calculator to evaluate this, be very careful. Make sure that you use enough parentheses. Make sure that you are just very careful that we don't make a silly mistake here. So let's see, in my numerator I've got 0.105. In my denominator, let's see, I have 1.5625. So 0.105 divided by 1.5625 gives me 0.672. Oops, 0.0672, excuse me, I missed a 0. 0.0672. So now I want to be able to talk about, what does this quantity represent? What does it mean? What is it trying to tell me? So okay, again, I'm going to start off the interpretation pretty much exactly the same way I did last time. I'm going to start off by referring to when we're talking about, what value of time we're talking about. And we're talking about a half hour after the injection. So a half hour after the injection, the drug concentration, so it's not the drug concentration anymore, it's how this drug concentration is changing, because we're talking about the derivative. So the drug concentration is, it's either increasing or it's decreasing. I gotta be able to tell which one. I ended up with a positive result, so I can tell that the drug concentration in the right arm, let's make sure we say that, in the right arm, the left arm, excuse me, in the left arm is increasing by this amount, by 0.0672 milligrams per cubic centimeter. And I want to talk about how often it's increasing by this amount by. I still need to give per unit of time every single time. Per, and then I believe my unit of time was hours. Let's just double check. Yep, T hours right there. So per hour, that's how quickly my drug concentration is increasing. So this is how I would interpret it. So for the most part, interpretation, even though we use the quotient rule, still exactly the same. We're still talking about the derivative. The derivative still represents the rate of change in the slope of the tangent line. We just need more tools to find the derivative in these new circumstances.